4.37 light-years. That is how close the nearest Sun-like star sits to Earth. In August 2024, the James Webb Space Telescope found a Saturn-mass planet there, in the habitable zone, where conditions for liquid water are at least plausible. By 2025, the planet was gone. 3 suspects: an orbit hiding it behind the star's glare, a ghost produced by the instruments, or a dust cloud that was never a planet at all. August 2026 is when the case reopens. The star is called Alpha Centauri A. It is nearly a perfect twin of our Sun, 1.1 times the mass of our Sun, the same surface temperature, and old enough that any planet around it has had billions of years to settle. If you could stand on a world orbiting Alpha Centauri A and look back toward Earth, our Sun would appear as a faint point of light in the southern sky. 14 trillion kilometers away, the nearest place in the observable universe that actually resembles home. For decades, every attempt to find planets around Alpha Centauri A ran into the same problem: the companion star. Alpha Centauri B sits close enough in the sky that both stars flood the same field of view, and no instrument had the contrast to separate a faint planet's warmth from that double glare. Then, in August 2024, the James Webb Space Telescope cleared that problem for the first time and found something that vanished before anyone could confirm it. This is the case of the disappearing planet next door. The detection is documented. The non-detections are documented. The 3 competing explanations are all scientifically defensible. The verdict is not in yet. Alpha Centauri is not one star, it is 3. Alpha Centauri A and B form a binary pair, 2 stars orbiting their shared center of mass on an 80-year cycle. At their closest approach in that orbit, they are 11 astronomical units apart. 1 astronomical unit is the distance from Earth to our Sun. 11 of those units is roughly the distance from our Sun out to Saturn. At their farthest separation, Alpha Centauri A and B reach about 36 astronomical units, comparable to Pluto's average distance from the Sun. By stellar standards, their orbit is wide and slow. The 3rd star is Proxima Centauri, a dim red dwarf sitting about 1/5 of a light-year closer to Earth than the binary pair. Proxima is technically the single closest star to Earth, at 4.24 light-years compared to 4.37 light-years for the main pair. It already has multiple reported planets, including the well-established Proxima b. But Proxima Centauri is a violent star. It erupts with ultraviolet flares powerful enough to threaten the atmospheres of planets close enough to be warm. It is the wrong kind of neighbor. Alpha Centauri A is the real target. It is a Sun-like star, over 4 billion years old, stable enough that any planet around it has had time to settle into a mature orbit. And until 2024, it was completely without a confirmed world in sight. James Cameron put the fictional moon Pandora in orbit around this exact system when he made Avatar. That was not a random choice. Alpha Centauri is the only stellar neighborhood close enough to Earth that the journey, while still impossible by current technology, produces a number a person can hold in their head. Cameron's writers knew the address. What nobody in 2010 could confirm was whether there was anything at that address. Now, 15 years later, the Webb telescope found something and then lost it. Finding a planet around Alpha Centauri. A means solving a problem that stopped every previous observatory, the companion star's light. Alpha Centauri A and B appear close together in the sky as seen from Earth. Even with the best instruments, both fall within the same field of view, their combined glare washing out any faint signal from objects nearby. The challenge is roughly equivalent to trying to photograph a firefly hovering 3 inches from 2 car headlights, seen from 2 miles away at night. The firefly is real. The headlights make it invisible. The Webb telescope carries a coronagraph, a physical mask inside the optical path that blocks the direct light from a single bright source and reveals dimmer objects in the surrounding field. Normally, it masks just 1 star. For Alpha Centauri, The team had to mask the primary star with the coronagraph, and then separately model and subtract the contribution from Alpha Centauri B, because the mask could not remove that second source. To do that, they had to model and subtract with extreme precision. That second step required building custom software for a problem no telescope team had previously needed to solve at this scale. The operations team at the Space Telescope Science Institute built a custom observing sequence specifically for this target. Charles Beichman of the NASA Exoplanet Science Institute at Caltech, co-lead on the investigation, said the extra effort worked better than they had hoped. What the cleaned images from August 2024 showed was a signal. It was given the designation S1. The team published the actual processed infrared data, not a simulation and not an artist impression. It was a blob 10,000 times fainter than Alpha Centauri A, sitting at roughly twice the Earth-Sun distance from the star. At that distance and with that estimated mass, S1 sits inside what planetary scientists call the habitable zone, the orbital range where liquid water could persist on a rocky surface. S1 itself is not a rocky surface. It is a gas giant, roughly the mass of Saturn, with no solid ground and no directly habitable environment. What it could have, given a Saturn-mass planet in a stable orbit around a sun-like star, are large moons. Saturn has more than 100 confirmed moons. If S1 is real and carries large moons, the question of liquid water on those moons is not obviously off the table. Aniket Sanghi, the Caltech doctoral candidate who co-led the analysis, described his team's reaction when S1 first appeared in the processed data. They had spent months testing it. Every attempt to explain the signal as an artifact, whether residual light from Alpha Centauri B, reflections inside the telescope's optical path, or a background object aligned by chance, failed to account for it. He put it plainly. The signal just popped out, clearly. Clear enough to publish, not clear enough to call confirmed. The team prepared 2 papers, submitted them to the Astrophysical journal letters, and arranged for peer review. Then they looked again. In February of 2025, the Webb telescope returned to Alpha Centauri A under the same observing setup. The image came back clean. No S1, not a reduced signal, not a faint remnant, just gone. The team applied for Emergency Director's Discretionary Observing Time, the kind of priority access that requires a direct appeal to the institute that runs the telescope. In April of 2025, they pointed the instrument at the same target. Still nothing. Sanghi's published description of the situation was blunt. We are faced with the case of a disappearing planet. This is the first moment the second suspect enters the room. The skeptics came in with a simple counter. One faint signal, right at the absolute limit of what the instrument can resolve, found with a subtraction method never previously used on this target, with no independent confirmation from any other telescope. That is not enough to call a planet real. The non-detections in 2025 do not just fit a planet hiding behind the star's glare. They fit a signal that was never a planet in the first place. Every telescope has ghosts, internal reflections, scattered light. Processing artifacts show up once in a specific observing geometry and then never repeat. If S1 was one of those, the silence in 2025 is not a mystery. It is just the ghost failing to come back. The team did not say the skeptics were wrong. They said the skeptics were betting on the less likely explanation. So they put the planet hypothesis on trial. They ran millions of simulated orbits through the data and asked one direct question. How often would a real planet on a gravitationally stable orbit in this system simply be out of view in both the February and April 2025 observation windows? The answer was 52%. In more than half of all stable orbits that matched the August 2024 detection, the planet would have moved exactly where Webb could not cleanly separate it from Alpha Centauri A's residual glare during both follow-up observations. The orbital path itself explains the silence. The telescope was not fooled. The timing was wrong. If that answer surprised you, the like button is right there. It is the fastest way to tell the algorithm this case deserves more eyes. 52% is not 95%. If you have a threshold below which you would call that a ghost rather than a planet, leave it in the comments. The team that found S1 has theirs. The skeptics have theirs. The number is the same for both arguments. Before this case goes into the cold case file, there is a bridge that belongs here. The video on this channel about the Kilonova collision, the one about the gold in your wedding ring, covered an event that already happened and left physical evidence in metal all of us can hold. What all of us are looking at now is whether the nearest sun-like star to Earth has a world in its habitable zone. A case still open and still live. Both are documented investigations. That is what this channel covers. Before the Webb telescope, there was a detection that nobody believed. In 2019, a team running the Very Large Telescope in Chile pointed it at Alpha Centauri A with a technique nobody had tried on this target at this scale before, chopping rapidly between the star and a nearby reference star to strip out the overwhelming background glow and reveal whatever was hiding underneath. It took nearly 100 hours of telescope time. At the end of those 100 hours, a faint smudge appeared at a position consistent with a planet orbiting at roughly the distance between Earth and our Sun. The team was careful. They published the result in 2021, called the candidate provisional, noted that instrument artifacts could not be ruled out, designated it C1, and flagged it for follow-up confirmation by other observatories. No other observatory attempted the follow-up. The technique was too new, the signal too marginal, and the community had seen too many Alpha Centauri false alarms before. C1 went into the archive. 5 years passed. 5 years later, Beichman and Sanghi's team noticed that C1 and S1, the 2019 ground detection and the 2024 space detection, were consistent with the same object on the same orbit. Two instruments, two entirely different methods, 5 years apart, potentially capturing the same planet at two different positions in its path. When the team folded C1 into their orbital simulations alongside S1, the combined data narrowed the possible orbital solutions considerably. The best-fitting paths pointed toward a period of roughly 1.5 to 2 years, an elliptical orbit swinging between 1 and 2 astronomical units from Alpha Centauri A. On that path, the planet's position in February and April of 2025 would place it inside Alpha Centauri A's optical exclusion zone, too close to the star's glare for the Webb coronagraph to separate it from the background. In August of 2026, the geometry reverses, and the planet should be back at a detectable separation, if it exists. The detection that nobody believed in 2019 became the strongest piece of supporting evidence for the 2024 result. The skeptics' counter is measured. Two signals, at the limit of two different instruments, both using novel subtraction methods, and both operating at the threshold of what each telescope could reliably resolve, on one of the most challenging targets in the sky. That is still not two independent confirmations. Artifacts driven by the geometry of a bright binary system can recur at similar positions, because the geometry that produces them recurs. Two ambiguous signals at positions consistent with the same orbit are not the same as two confirmed detections. The investigation team's reply is this: generating the same artifact at a compatible orbital position with two separate instruments, 5 years apart, requires a specific geometric coincidence, and that becomes less plausible as the positional constraints tighten. The simplest explanation for two position-consistent signals 5 years apart is an object moving along a consistent orbit. August 2026 will test that explanation. The third suspect, dust, requires some consideration. Alpha Centauri. A likely carries exozodiacal dust, the fine material that produces the faint glow around our own sun. The Alpha Centauri system is old enough and settled enough that a dense concentration of that dust is not the first thing anyone would predict. But Webb's heat-sensing camera detects infrared light, which is exactly the kind of signal warm dust emits. A dense enough clump, at the right angle relative to the coronagraph's inner boundary, could in principle produce a thermal signal at a level consistent with S1. The team modeled how concentrated the dust would need to be to produce S1's brightness without spreading to fill the surrounding field. The answer was an unusually high concentration at a specific location, without a corresponding diffuse halo extending outward. Physically possible, but requiring a specific set of conditions, neither confirmed nor eliminated. The weakest of the three suspects, but still in the room. 3 interpretations, 1 dataset, no resolution until the telescope looks again. Before the planet can matter, it needs to be able to exist. A binary star system should, in principle, make stable planetary orbits difficult. Alpha Centauri B pulling on any planet around Alpha Centauri A from a varying distance of 11 to 36 astronomical units is a real gravitational influence worth taking seriously. The orbital mechanics, however, favor stable conditions in the inner region. Computer models from multiple research groups show that planets can hold stable orbits for billions of years, as long as they remain within roughly 2 to 4 astronomical units of Alpha Centauri A, and stay in approximately the same plane as the binary. Beyond that range, Alpha Centauri B's gravity accumulates perturbations that can turn circular orbits chaotic over geological timescales. S1 at 1 to 2 astronomical units sits inside that stable zone. The companion star's pull from 11 plus astronomical units is real but manageable, the same way Jupiter's gravity does not destabilize Earth's orbit, even though Jupiter holds more mass than every other planet in the solar system combined. Both Alpha Centauri A and B are also old stars, past 4 billion years. Whatever orbital arrangement existed around Alpha Centauri A has had 4 billion years of gravitational disturbance to settle. The unstable orbits were cleared out long ago. If S1 is a real planet, it has earned its position. It has room to exist. This is where the travel numbers become humbling. The Parker Solar Probe, currently the fastest object humanity has ever launched, moves at approximately 700,000 kilometers per hour at its closest pass to the Sun. At that speed sustained in a straight line, which is impossible but useful as a benchmark, a one-way trip to Alpha Centauri A would take roughly 6,000 years. Voyager 1, launched in 1977 and currently past the outer boundary of the solar system, moves at about 61,000 kilometers per hour. At that speed, the same trip takes between 73,000 and 100,000 years. Both spacecraft will be inert metal long before they cover a meaningful fraction of that distance. Breakthrough Starshot is a research program launched in 2016, funded by private investors, including Yuri Milner, and backed in its early stages by Stephen Hawking. The concept is a fleet of probes weighing a few grams each, lighter than a paperclip, equipped with a reflective light sail roughly the area of a postage stamp. A ground-based laser array producing 100 gigawatts of power accelerates each probe to 20% of the speed of light in a matter of minutes. At that speed, the one-way transit to Alpha Centauri A takes 20 years. The probe images whatever it finds, transmits the data back at the speed of light, and the signal reaches Earth 4 years later, 24 years from launch to first close-up data from another stellar system. The full system does not yet exist. The underlying physics holds up. Getting there is an engineering problem and a funding problem. If S1 is confirmed in August of 2026 as a real planet in the habitable zone of the nearest Sun-like star, Breakthrough Starshot has a specific destination. If you think a probe launched in the 2040s could reach that planet before the end of the century, leave that in the comments. If you think it will never happen in any of our lifetimes, leave that too. In 1955, 2 years before the first artificial satellite reached orbit, the concept of directly imaging a planet around another star was not scientific aspiration. It was science fiction, and not the most plausible kind. The contrast ratio required to see a planet next to its star, suppressing the star's light to 1 part in 10 billion while preserving the planet's faint warmth, had no instrument associated with it. It was purely theoretical. In August of 2024, a telescope that had to invent a custom operating procedure specifically for this target captured a signal 10,000 times dimmer than its host star at the nearest Sun-like star to Earth, 4.37 light-years away. The time between those two sentences is 69 years. Anyone watching this video who was born before 1956 was alive for the entire arc, from no satellite in orbit to a possible photograph of a planet at the nearest star like our own. If you know someone who lived through that whole run, send this to them. That is exactly what the share button is for. The case is not closed. S1 is a candidate, not a confirmed world. The strongest supporting evidence, the 2019 Very Large Telescope detection, is itself provisional. 2 of the 3 suspects remain viable. The debate is active in peer review as of the date of this video, and the scientists on both sides are serious researchers working from the same data. In August 2026, the Webb telescope is expected to point at Alpha Centauri A again. If S1 appears at the position the orbital models predict, the artifact explanation loses most of its remaining support, and the planet is effectively confirmed. If S1 does not appear, the question becomes more complicated. Either the orbit model was wrong and the planet exists on a longer or less predictable path, or the 2024 signal was never a planet, and the case moves to the unsolved column. A third outcome is also possible. The telescope could find something at a position that does not match any of the current orbital predictions. Not S1 exactly, but something in a different configuration that changes the framing of the entire case. That outcome has a low probability, but is not excluded by the current data. The August 2026 window is not indefinite. What the team needs is specific: a point source infrared signal at the position the orbital models predict, at the brightness consistent with the August 2024 detection. A faint hint at the wrong position, or nothing at all, keeps the case open. The observing season during which Alpha Centauri A is positioned correctly for Webb's coronagraph lasts only a few weeks. If the telescope does not secure time during that window, the next opportunity pushes out by roughly a year. The teams working on this case have submitted observing proposals. Whether they receive time depends on the Space Telescope Time Allocation Committee weighing competing scientific priorities. The Nancy Grace Roman Space Telescope, which carries a coronagraph built specifically for nearby star systems and is expected to begin operations in 2027, could provide an independent second look even if Webb does not get the window. If both telescopes observe and reach the same conclusion, the case closes. If they disagree, the investigation continues. Whatever 2026 returns, the image from August 2024 is already a document of what humanity can currently see. Pointed at the nearest address to our own in the observable universe, at the very edge of what the instrument could resolve, something was there. 4.37 light-years is still a distance no human will cross in any of our lifetimes. That is the closest the sky gets to putting something next door, and something was there. Leave your verdict in the comments. 1 sentence. Real planet hiding behind the star, instrument artifact, or a third explanation none of the 3 teams have named yet. If you want to be here when August 2026 delivers the verdict, the subscribe button is right there. This case is not finished.